Alright, let's finish this thing. Alright, so as I mentioned, the differential is a linear transformation from Rn to Rm in this context, which means that it has a standard matrix. The columns of the standard matrix are just given by the differential acting on E1, E2, E3, E4, En respective. Those are exactly the partial derivatives with respect to 1, x1, x2, xn. This gives us an n by n matrix. You can also repackage it as a stack of gradients, the gradient of the first coordinate component function, the second component function, the mth coordinate component function. I got to transpose them to make them into rows, but I mean both of these viewpoints are useful. Sometimes to look at the Jacobian matrix as a bunch of columns glued together or as a bunch of rows glued together. And you see both of these appearing in applications of the Jacobian matrix to other things. That's why the gradient shows up in like Calc 3 looking at functions from R2 to R. And these things show up when we're looking at coordinate change, of course. It's a little bit more obvious. You have these sort of things when you look at coordinate change in Calc 3 that shows up. Now what I'm doing now is just working on a specific example of how to find the Jacobian matrix for a specific function f, which is going from R3 to R2, it looks like. So it would be a 2 by 2 rows by 3 columns matrix. Partial f, partial x, partial f, partial y, partial f, partial z. I'm going to get 2x from this one. I'm going to get 0 from that one in the first thing. Now, you should understand my notation, just like in my linear algebra class. This is actually a sneaky notation for a column vector, right? X squared plus y squared and yz. So again, like I was saying, 2x from this, 0 from that. With respect to y, we get 2y. With respect to y here, we get just z. Partial f, partial z. Well, there's no z component in the first component here, so that gives us 0. And this one, there is a z dependence, that gives us y. Partial differentiating, alec calculus 3. And I guess I should emphasize, what we're doing here is just trying to understand an abstract theory of calculus, right? ultimately, that's all we're doing, is just trying to understand how to do calculus for normed linear spaces. We know from calculus 3 how to do it for R2 and R3, and we're just continuing that story here, really, but with the benefit of linear algebra. Now, the other thing to think about is in Calc 3 you find gradients, or in Calc 1 you find derivatives, and then you can construct a tangent line. The tangent line is the best linear approximation, or the so-called linearization, of the function at the point of tangency. In the same way here, I can use this Jacobian matrix to construct the best linear approximation to the function, the mapping you might say, from R3 to R2. I pick a point, 1, 2, 3. And then what I do is I plug in the point 1, 2, 3 into the Jacobian matrix, which is sometimes called the derivative. Although I try to make a distinction of the derivative being the, I'm trying to remember. Oh man, I'm fuzzy. Anyway, Edwards makes a distinction between the derivative and the differential, if I recall correctly. I think, well, let me not speculate. I'm a little rusty. Anyway, f of 1, 2, 3 plus f prime of 1, 2, 3 times the x minus 1, y minus 2, z minus 3, and then you plug in the point, 1, 2, 3, 1, 2, 3, and after a little bit of writing, skip ahead a bit here. Yeah, that's fascinating. We can all do that. So you multiply the matrix, you add the point, and there you go. That's the best linear approximation to that function, that nonlinear function at the point 1, 2, 3, based on using the Jacobian matrix, which of course is tied to the differential. This gives us the best linear approximation to the function. Now, what I'm going to do in the next lecture, I'm going to talk a little bit about now, I believe, is just this theorem, which is that if we have a continuously differentiable function at a, then f is differentiable at a. And that's a very nice thing, because continuous differentiability just involves partial differentiation, which is pretty easy, whereas differentiability involves that big bigger multivariate limit. Although the continuity of the partial derivatives is also inherently multivariate, so it's not completely for free or anything. But this is nevertheless a nice result, and it takes me about 20-30 minutes in the next lecture to prove it, if I remember right. So, let's see, do I say anything else? Oh, stop that. I think that's pretty much it. And the point of course, is again, we use the vector limit theorem. If I can prove this theorem for a component function, then I have proved it for the whole thing because of the vector limit theorem. So, all right, well, I hope this was marginally helpful. I've tried to add sound. I'm going to leave this one and the other one up just for the sake of not, I don't know, I'm not sure which is more profitable to watch, this one or the other one, but there it is.